All right.
Yeah, please.
Should we start? Okay. Okay, so what I'll be talking about today is a bit of a different aspect of what was covered in the first talk. In the first talk, we heard a lot about physical applications of rare events, a lot of instances where they pop up. I'll be talking about a particular algorithmic development that I've worked on for a while now. It's part of a side project that I'm carrying out with a couple of people in Germany. Luca is also involved in this project, as well as a PhD student of Luca, Georgios. He is in the audience. Let me give you a small introduction to what I'll be talking about. So what we attempt to construct here is an effective action for hydrodynamics, stochastic hydrodynamics to be precise, in the presence of fluctuations. And we want to sample this effective field theory in terms of a Markov chain Monte Carlo algorithm. Now, as we heard in the previous talk, there are certain problems where one might ask what kind of configurations might dominate and contribute in a very extreme manner in terms of strong fluctuations. And phrasing these types of problems, stochastic problems, in terms of a Markov chain Monte Carlo algorithm, we might, or in terms of a field theory action to be precise, we might play the game of systematically modifying that action to highlight particular field configurations. So this is what is essentially driving this project, the idea to have an algorithm at hand which allows us to do a systematic modification of the action. Now, there's different ways to do this, which have been explored in Euclidean Monte Carlo algorithms, not in the context of rare events, but in other types of problems. Here, I will take a look at a particular way to define such an algorithm for non-equilibrium systems, and in particular, systems that do not conserve energy. So we will show that these algorithms are able to capture the properties of stochastic hydrodynamic flow in both regimes where the flow is regular, laminar, or where it is highly erratic, related to turbulent flow. So surprisingly, at least for me, coming from a field theory side, we saw that these types of algorithms of Euclidean Monte Carlo are not directly transferable to a non-equilibrium setting. And there's a specific type of tuning that you have to do to capture the strong fluctuations that are so characteristic of turbulence. All right. So given of what I told you in the introduction, the agenda is clear for us. Our basic setup of the system we want to study is a set of equations which are related to first-order hydrodynamics, and in particular, we have three types of conserved quantities. And to these conserved quantities, which are the mass density, the energy the mass, the energy, and the momentum, we add stochastic terms which are captured by the heat flow and the external stress. Now, what do I mean by stochastic? In particular, we will be looking at Gaussian fluctuations. However, we're not going to assume that these Gaussian fluctuations are necessarily delta correlated. In particular, if we want to model turbulence, we can assume them to be strongly correlated over a large range of scales. And we will see that this induces severe complications if one naively looks at these types of systems in terms of a Monte Carlo framework.
If you have a viscous stress tensor, then how you have energy having a continuity form? It must be dissipation of energy.
Yeah, so if you have the gradient terms here, you have a dissipative contribution, yeah.
No, but your dt epsilon is a divergence of J, which already in gradient form, right? It shouldn't be. It must be some kind of term which is not gradient.
Which is non-gradient. You're saying that the dissipative contribution should be a non-gradient contribution?
There is a gradient part of viscosity, but it's also non-gradient, which is dissipation, which does not disappear after you integrate over space.
Well, I mean, this is actually, this contribution is exactly what you find in Landau and Lifshitz. So if you want to argue, you should turn back to Landau, I guess.
He considers also the heat equation.
Yes.
He considers also the heat equation. The whole is a very general writing for.
Exactly.
The total energy.
It's a systematic, yeah. It's a systematic expansion in gradients. It's pretty standard. All right. So let me phrase this set of equations. It's just a particular example of a set of equations that one might be interested in. Let me try to rephrase them in a different language, a language which is more familiar from my perspective, in terms of a functional integral that we might then use to set up a Monte Carlo algorithm. So I'll be defining a set of hydrodynamic degrees of freedom, which I will label by capital phi. Now, A is not a single representation of a vector representation of a particular field. It's a superindex which includes scalar fields, vector fields, or maybe Grassmann-valued fields. This is really free, something which we are free to do. I'll be very imprecise in that manner. But it allows us to reduce the complexity of what we saw in the previous slide. In particular, all what we saw on the previous slide reduces down to this equation and can be captured by this approach. Notice that, as we saw in the previous talk, there's a particular assumption going in here, in particular the nonlinear interactions, which are typically in here, will be of a non-gradient form. So this is not a stochastic Langevin equation which always converges, which can be shown to always converge to a stationary state. This object here is very much more complex. Of course, it will depend on the particular hydrodynamic model that we're looking at, and we will look at a particular system, a simple system where we can test these methods later on, but let me just leave it fairly general at this moment. And let me assume that this equation admits a unique solution. So for all times in a given spatial domain in d dimensions, and for any stochastic realization of the random force on the right-hand side, this allows us to write down this identity. We can write the one in terms of a functional integral with respect to the hydrodynamic variables and an averaging, ensemble average, over the realizations of the stochastic force. So I choose a measure in such a way that the normalization condition is satisfied, so the measure for the stochastic forcing. And by a simple change of variables, I can write this delta function here in terms of the original equation of motion. Now, when I do this transformation of variables, I generate a functional determinant, which is, in this case, expressed in terms of this operator here. And typically, if we are interested to solve this functional integral, we will have to take care of this functional integral in an appropriate manner. So let me be a bit more precise. So as I already alluded to, the stochastic forcing we'll be considering is assumed to be Gaussian. I'm assuming, furthermore, that it's centered. So there's no difference between the connected or unconnected two-point functions. And I will let the forcing to be wide in time, but non-local in space. So in general, this might be a very complicated kernel. So this is the correlation function that characterizes the stochastic forcing. And what I will do is I will write the functional determinant that we got by doing the chains of variables in terms of Grassmann variable fields. Right? So if we expand the exponential, we can reduce the term on the right-hand side in terms of one expression apart from the one. And that is exactly the determinant. So by doing this, we are basically done, right? Carrying through the stochastic average using the fact that it's Gaussian. Using this representation of the functional determinant, I can calculate this expression here and read off an effective action for hydrodynamics. Now, one thing you should notice, it's just an expression of the identity. So by itself, it's pretty boring. But of course, we want to include fluctuations into the system. So in particular, to be precise, we want to perturb the system and look at correlation functions. And then, of course, we can get access to non-trivial information that is captured by the dynamics that we're looking at, so by this object over here. Now, you see that you might guess that we have overcomplicated things because we started with one set of hydrodynamic variables, but now we have 3 more, a so-called Lagrange multiplier field, 2 Grassmannian fields, which are not necessarily conjugate to each other. Why should we do this? Well, as already said, this gives us the possibility to modify this action for purposes to highlight specific field configurations that might dominate the dynamics in a given sense. So this equation of motion down here. Now, just as a small reminder, or just to give you a different perspective, how a field theorist sees this procedure here, this goes by the name of gauge fixing, or BRST symmetry in the field theory literature, and is essentially just the statement that we are looking at a stochastic field which has a shift symmetry, and given that we are only interested in boundary data, for instance at t equals 0 or t equals capital T, we want to make sure that we don't integrate in the functional integral over all possible gauge copies allowed by the shift symmetry, but instead we pick out a single representative of the many gauge equivalent copies, and this is just a single section of all gauge orbits. So this is what we call gauge fixing, and if you do this gauge fixing by a gauge function which takes this form, our original equation of motion, and implemented via phi tilde, which is the Lagrange multiplier field, we arrive at this action. Now, you see it has the same field content. It has the psi tilde field, phi, and phi tilde field. But in this writing, a particular symmetry of the action is apparent, which was not there in the previous writing. So in fact, we can construct these actions in a very concise way by realizing that these actions allow for particular symmetry operations by which actually, if this were a Langevin equation, we could use the symmetry to prove certain aspects of the dynamics of the system. So for instance, in a quantum field theory context, if this were a Langevin equation, one can show that the Langevin dynamics dimensional reduces. So in the long time limit that you converge to a particular distribution. For general L, this is not, at least to my knowledge, possible. So we'll now leap forward onto a lattice definition of this theory. Up to now, everything that I've said is completely formal. So of course, we want to give these words somewhat of a meaning. So in this sense, I will define the fields on a regular hypercubic lattice. And this essentially states that we introduce the UV cutoff, an ultraviolet cutoff, both in space and time for the theory that we're considering. Of course, for hydrodynamics, this is perfectly valid. Hydrodynamics is in itself an effective theory, so there's no need to push this ultraviolet limit to infinity. It is by itself defined with such a cutoff. Such a cutoff is always implied. But however, note that there's one thing that really troubles someone coming from field theory, namely that this procedure is not as straightforward as one might think it is. In particular, one worrying aspect in this case is that the symmetries of the system are not satisfied exactly. In a lattice discretization, we do not preserve, for instance, the Galilei symmetry, which is so essential to provide the dynamics of Navier-Stokes equations. In particular, we have a generalized Galilean symmetry for the stochastic versions of hydrodynamics, and additional continuous symmetry operations which are not satisfied in this particular choice of discretization when we put the fields on single sites of a regular lattice. So in particular, if one adopts such a definition of the theory, one really has to ask if the discretization, the choice of discretization that one uses introduces relevant perturbations to the model that might, in fact, lead the system, if one goes through a renormalization group procedure, for instance, to a completely different fixed point. In fact, we'll see at a later point in this talk that there might be indications of such behavior. Now, a Markov chain Monte Carlo uses this object that I've just defined, the action for the system, to to suggest new field configurations that are randomly generated by a Markov process. In particular, what we are looking for is a stochastic mapping that is ergodic. So we want to explore the complete phase space of the model by applying a set of operations which are sufficiently ergodic so that we do not stick in one part of the configuration space. So this mapping, if we apply it once, will generate a new configuration, and this new configuration will depend only on the previous one. There's no memory effects. That's what we mean by a Markov procedure. Of course, we want to make sure that after a sufficiently large number of iterations, optimally they should be small, we sample the stationary distribution. And in fact, we can make sure that this is satisfied by checking that the algorithm that we construct satisfies detailed balance. So this can be done by using a metropolis accept-reject step. After each suggested update of the fields, we accept the new update by making this by accepting it with probability p, where the probability is given by the minimum of e to the minus delta s, where s is simply the difference in the action for the previous field configuration and the new suggested field configuration. Of course, to prove ergodicity for a particular algorithm is a bit more complicated, but we'll look at a particular example where it can show that this holds. Now, the previous action that I showed, I already told you, that, or you might have thought that it's not very beneficial if one wants to do any sort of computational exercise with that action. It was nice to see the symmetries, but we introduced 3 additional field degrees of freedom, in particular Grassmann-valued fields. How could you possibly simulate that on a computer? Well, in fact, the Grassmann-valuedness is not really a problem, but the problem was that this particular action that I wrote down does not lead to a positive definite probability measure. So how can we evade this problem and work around it to define a Monte Carlo algorithm to sample the probability distribution? Well, we'll simply integrate out those additional fields, and we can show that this is possible under certain assumptions. First of all, we want to make sure that the inverse kernel K exists, and in particular in the following, we will choose a particular definition of the Heaviside theta function at t equals 0, which implies that a particular discretization for the action should be used. So in that particular case, we can integrate over all these the auxiliary Lagrange multiplier field phi tilde. The functional determinant drops out, so we arrive at an action which is manifestly positive, right? So it's just the square k to the minus 1 is assumed to be a positive definite kernel too. Now, Monte Carlo in equilibrium systems is typically carried through by looking at local updates of spins, if you think about the Ising model, for instance, which are then accepted via or rejected via the metropolis step. However, such an update procedure will carry through a random walking configuration space, and of course that might be good if you're far away from a critical point, but as soon as you have long correlations in your system, your update will get increasingly bad. In particular, if you encounter such a situation down here, it will take of the order of the spins included in these block sizes here, the white and black blocks here, to suggest a statistically independent field configuration. At the critical point, you have critical slowing down, so you have to think about other types of algorithms that might sample the configuration space more efficiently. So for spin systems or continuous field, the ON theories, for instance, there have been different algorithms that were designed exactly for that purpose, so-called cluster algorithms. For hydrodynamics, what we'll be looking at here, it's a very similar situation since, of course, we have a large range of scales that we need to explore, and we're running into the same problem. So in general, we cannot apply the standard local update schemes that we use in conventional spin systems away from the critical point, but we need something that updates fields globally and makes large steps in configuration space. One particular way to do this is to apply a trick, and in particular such a trick where we write the original path integral in this way written down here. So you see the only difference is that we multiplied or included an integral over these pi fields, which we might call momenta. They, of course, have no relation to the actual conjugate momenta to the phi field. But you see that introducing this, these fields pi in here, we might write the original path integral in a form that is very much like in a Hamiltonian, an effective Hamiltonian for the system. Now, of course, now we can use this fact by suggesting new field configurations by applying a molecular dynamics algorithm on the hypersurface provided by this effective Hamiltonian. So we will look for a new configuration on this hypersurface, and by that we make large steps in configuration space because we avoid that the algorithm really just carries out a random walk around one particular configuration that we started from. This is done by a symplectic integrator, which conserves energy, so effective energy up to order epsilon squared in the step size. This is the particular scheme that we might use. And to make sure that, that the algorithm is exact, independent of the step size, and in particular satisfies detailed balance, we'll use the metropolis accept reject step at each time when we finish one trajectory on the hypersurface. Now, ergodicity is taken care of if we resample these conjugate momenta after each trajectory, and thereby, in principle, we should be able to explore the full configuration space that the system has to offer. Too bad it doesn't work. In this particular case, we had thought about an algorithm that provides global updates, but it turns out if you use this, you still run into a brick wall. The problem is due to the nature of the stochastic forcing that we include in our hydrodynamic model. In particular, it applies only in certain cases. If the stochastic forcing is delta correlated, everything's fine. Actually, the previous algorithm will work. As soon as you introduce large non-local fluctuations, you run into problems. So let us consider a different type of update or different type of model where we introduce these conjugate momenta. Of course, you can always perform the Gaussian integral, so you always it's perfectly equivalent to the
stochastic forcing is delta correlated in what? In space?
In time. But if we would assume that it also is delta correlated in space, then this algorithm would be perfectly sufficient. Yeah.
That would be equilibrium.
That would be equilibrium, yeah. So it's yes?
Can you explain how pi is coupled to phi?
Pi is not coupled to phi. It's just related to phi via these equations of motion. There's no pi dependence in S. There's no interactions between phi and pi. All right. So, of course, adding this piece to the action is something we can always do since we can always integrate out the field again. So I could easily write down an ansatz which looks like this as long as I make sure that the kernel is positive semi-definite, right? So it turns out that by using this freedom, we can cure the problem that we saw in the previous example. I will show you later on in a particular model where we play around with this modification. Now, what does this modification correspond to, or what does it allow us to do? Well, let us use this Hamiltonian, write down the equations of motion, and do a rescaling to bring it back to this form. What we have done by that procedure is we have introduced a new step size for the problem, a step size which I call epsilon tilde, and this step size becomes mode dependent. So if we go, for instance, in Fourier space, we will see that each Fourier mode of the field and these conjugate momenta that I find depend, that each of these Fourier modes has a different step size. So this, in particular, takes care of the problem that this contribution here on the right-hand side, the force in the molecular dynamics that acts on the conjugate momenta, is heavily dominated by the choice of the non-local forcing which goes into S, right? So if we take a look back at the action, it's essentially this object which leads to these very strong, very non-local effects that, of course, lead to disparate scales in the forces that enter here for very different modes. So by applying this trick, over here, by applying this trick and making sure that this force contribution to the conjugate momenta is always of order of epsilon, we can cancel this problem. Okay? Of course, this implies that we have to choose this kernel omega in this particular way to match the forces that enter the molecular dynamics. But as soon as we've done that, we can start simulating. Of course, this requires some tuning, but we'll see that this is possible. So to check the viability of this method and to see how it works in practice, we use a very simple model which has been used in various contexts. It's the stochastic Burgers equation in 1 + 1 dimension, and it's driven by a stochastic forcing, which we assume to be non-analytic, power law correlated. In this particular form, the exponent y is a free parameter in our simulation, so we will set it to different values. Thereby, we will see that this problem we just talked about is going to be more or less severe, and of course will lead to very different physical effects. As it was mentioned, in a particular range of values of y, we will see that the system actually allows a fluctuation dissipation theorem, so that would correspond to equilibrium fluctuations, which are plugged into the equation of motion. And in the other limit, we will have strong non-local effects, and we will see that this leads to some type of behavior which is very much like turbulence, although very different in practice. Now, what we will do is we will have to ask what are the physical parameters of the model. So for fixed initial and boundary conditions, we have two parameters that are physical. One is a dimensionless coupling, which appears if we would, for instance, apply some diagrammatic expansion of this field theory, the field theory defined in terms of the action I introduced earlier, and the exponent y, right? Two dimensionless parameters. So between the values 3 and 4 of y, the stochastic forcing has a probabilistic interpretation, so we can show that this relates to certain fractional Laplacians. This is not the case when y is larger than 4. That's when the forcing becomes infrared dominated, and that's when actually effects come into play which are very much like turbulence and what we want to study. And as already mentioned, when y equals 1, that's when we have the fluctuation dissipation theorem. Now, let's take a look at the performance of the hybrid Monte Carlo, which I introduced just now. It's the combination of the molecular dynamics that we looked at, plus a metropolis accept reject step, and on top of that, a resampling of the momenta to make sure that the algorithm is ergodic.
What is y here?
Y?
Yeah, parameter y.
Y.
The exponent.
Yeah, this
Yeah,
one.
it's
Oh, here in this particular setup, I think in this particular setup it was 4.
4.
Yes.
Okay.
Yes.
So real turbulence.
Yes. Yeah. So all the examples that follow have been done for y larger than 4, larger or equal to 4. All right. So in this particular case, we'll be looking at a very simple setup just to make sure that everything works. No nonlinearities, just a diffusion equation, but stochastic forcing. So the fluctuations are purely Gaussian, and we will take a look. So beta is in fact a parameter which measures the strength of this omega here. We will check the beta dependence of our algorithm. So beta is a tuning parameter which essentially measures the strength of this omega, which is tuned to match exactly the momentum dependence of the stochastic forcing, the kernel k. And by choosing the parameter of beta, we see that the algorithm can be extremely sped up, right? So setting beta to 1, which would correspond to a naive setup where omega would be almost equal to 1, you see that the algorithm moves very slowly in configuration space. So if we record measurements and look at our field configurations, measure, for instance, this effective Hamiltonian that I defined, we will see that it will take a very long time to reach a stationary state. However, simply by adjusting this one parameter, we can make sure that it's almost instantaneously there, and we can start measuring. Of course, we should always look at the acceptance rate as in any Monte Carlo algorithm, so we cannot play this game to speed up indefinitely. At some point, the acceptance rate will drop because we're making too big errors in the Monte Carlo procedure. But nevertheless, there's a lot of room here to work with. So let us see how this works out. A different check we have to do is that we don't have any drifts, right? As soon as we have reached this plateau, we want to make sure that there's no errors in the effective Hamiltonian that accumulate. So you see after a short relaxation stage of the algorithm, we reach the stationary state, and then we have fluctuations around 0, which is good. Another thing, which is the ensemble average of e to the minus delta h. This should be exactly 1, which is related to the exactness of the algorithms, a crucial property of the stability of the algorithm. So this is something you also want to check, and it works out. So that's a nice procedure. Another check you should always do, very much like in equilibrium Monte Carlo situations where you might start from different ensembles. Here, this role is played by the initial conditions that we use for a space-time history, right? So remember, we're sampling space-time histories of the velocity field. So a configuration which is two-dimensional, and at each Monte Carlo time step, we will get a new suggested space-time history. And for each of these space-time histories, we have to specify what happens at the first slice, time slice, right? This is what we mean by initial conditions. So if we use a sinusoidal initial condition, for instance, we will see that the algorithm shows the same behavior as before.
At the last.
Sorry?
Also at the last.
There's no boundary condition at the last.
Okay. But in principle, you could.
Oh yeah. Well, yeah. Good point. I'll mention this at the last later on. Of course, yes. So maybe I'll just point this out here because this is actually an important point. Of course, sampling space-time histories gives us a lot of freedom to play with the dynamics, not only by defining the action, but by defining the boundary conditions. So if you do a direct numerical simulation, of course, you provide the initial conditions, you provide the spatial boundary conditions, but you have to wait and see what happens at large times. Here, you do not have this. You can actually play around with the final time constraint. You can impose a particular condition that the configuration should reach a final state, and now you can let the Monte Carlo decide how it wants to get there. So this is a particular way to modify these methods to allow us to sample transition probabilities between two different states. And the algorithm then explores the phase space of that possibility. Now, but as already said, this is something that you can build on top. Here in this particular case, it's just the initial conditions that we modified to check that, as in usual Monte Carlo methods, you will reach the same stationary state. So as before, we should run into 3.2 times 10 to the 4. Here it's exactly the same behavior. You see that there's a small dip, but after a certain while, you should run into the same stationary state. You see the same behavior of the acceptance rate. And in fact, if you rescale the curves with this tuning parameter that I introduced that takes care of the non-local correlations in the system, actually we can see that all the data collapses, at least beyond a certain, in the long time limit. So you can play this game with a large range of parameters. You can change the initial conditions. You can change the viscosity. You can change the forcing. You will always see this universal behavior for the Monte Carlo algorithm. So this tells us that the Monte Carlo procedure that we designed is always runs, and this is with an asterisk, I'll mention an exception in a moment, always runs to a unique steady state in which we then start measuring in the ensemble, right? So then we start extracting correlation functions, all types of information that might tell us something physical about what is going on in the system. All right, so let me tell you what other checks you can do. Switching off, making the stochastic forcing small in amplitude. You can check that, of course, the analytic solution should be reproduced in the case for a given initial condition. This is sorry. This is satisfied. But as already said, there are certain exceptions to what I've just said, and this is something very important and which was a hard lesson we had to learn. And in particular, you have to take two facts into account. One, there's one particular way of doing equilibrium Monte Carlo, and that there's a particular thing you have to keep in mind when you do equilibrium Monte Carlo, and that concerns the initial configuration that you start your Markov chain with. Right? So this is known as hot or cold start. You might initialize your field to be 0, and then the random fluctuations start to come into your system, and they then lead to interesting configurations that are suggested by the action. You could start equally well from an infinite temperature ensemble. That doesn't really play a role. So randomness is a generic feature of the Markov chain. It does not make any difference usually. Here in this case, this is very different. So if you would, by any chance, think that you might initialize your Markov chain by a randomly chosen ensemble with no smoothness in the velocity field configuration, your Monte Carlo algorithm will blow up. All right? So in particular, what this means in physical terms is that we generate an unstable mode in the system, which then messes up the Markov chain. So this is actually something that I wanted to show by this at this point. So this should work now. Oops. So what I'll show now are 3 runs with different viscosities, in fact, where we will see how the Monte Carlo performs. So this is the largest viscosity of the 3 examples I'll be showing you. Note that this is a complete space-time history of the velocity configuration. So this is time, physical time. This is physical space. And now the Monte Carlo will explore all possible configurations that are allowed with the choice of the stochastic forcing that we use. In this case, y is 5, by the way. So it's a bit more long-range correlated than the standard Kolmogorov turbulence example in the Burgess case. All right, so you see that there's a particular structure in here that seems to be dominant around it. There are a lot of fluctuations, and the algorithm seems to nicely explore what is going on. Now, this is another example. A slightly smaller viscosity. You see that the fluctuations don't seem to be that large anymore, but you see that there are particularly dominant configurations, dominant structures in the flow that seem to evolve, which is good. So you really want to see that something like a shock evolves, right? So far, everything seems to be good. The third example is something like this. So this is the smallest viscosity in the system, and the similar behavior is seen if you supply enough randomness. So if you break the smoothness condition, you get an unstable mode, right? So somehow you pinch a shock in this particular case because of the fact that it's Burgess dynamics. A shock is generated, but the energy of the shock cannot be dissipated. It leads to an instability of this configuration, and if you let your simulation run indefinitely, of course, this instability will just grow and grow, and you shouldn't waste your computational resources. All right. So let me go back to presentation mode. So this is one problem you should always keep in mind. It's not equilibrium Monte Carlo. Here we are looking really at dynamics and the way that you choose your initial conditions, in particular for the configuration as well as for the initial configuration from which you start your Markov chain, are important. The second thing concerns the choice of discretization, which is, again, something which doesn't usually pop up in equilibrium Monte Carlo. Here, it might lead, in particular in the case of non-interactions, might lead to unconditionally unstable dynamics. So you might actually choose a discretization of the action that we looked at previously. You would guess that it's perfectly fine, well-defined. It has a continuum limit that you can take without problems. But in fact, that discretization will never lead to stable dynamics. It features an unstable mode, which will always grow. So you have to keep this in mind if you want to do these simulations. There's a lot of knowledge about what particular discretizations to use, and you should take a look at this. All right. So just to illustrate what can go wrong, in particular in the first examples, we chose a forward time advancing scheme for the Burgess equation. which takes this particular form. So d hat is just a discretized spatial derivative versus a backward time implicit discretization. And of course, the change is obvious, right? So this is the backward time implicit scheme. This is the forward time scheme. You see these very strong spikes here where just energy is accumulated. And if your configuration would be long enough, you would see that these spikes just grow indefinitely. So you just have to take care that this is satisfied. So let me just give you a short flash of what you can do with these measurements. So what we look at are velocity field differences and their respective local scaling properties, as well as 2- and 3-point correlation functions in the system. And in particular, I will be showing you 2 examples with, where we look at the moments of velocity differences for an ensemble with y equals 5. So this corresponds to a non-Kolmogorov type forcing, but which is more non-local. So it's a k to the minus 2. In here it's a, so it's p to the minus 2, right? All right, so what we show here are 2 rows. In the first row, that's at small physical times in the configuration. The lower row is at late physical times in the configuration. So you see that there is this a very distinctive feature that appears at late times, right? So in contrast to the initial time behavior, which is very close to the initial conditions that we supply, at late times the dynamics has taken over. So the forcing has started building up the configurations. The forcing leads to interesting dynamics. And in particular, we might extract scaling exponents, the local scaling behavior of the system. So this is the scaling spectrum that we can extract from these previous plots here. You see that we are very nicely resolved. So we run to the limits provided by the dimensional scaling given by the Laplacian. And at intermediate separations, we run to a plateau provided for the higher order structure functions, so from order 2 to 5. So before I continue, let me just point out, however, this last column down here, this is the measured autocorrelation time in the system. So for each of these structure functions, we have a data point, and we have to estimate our errors. And in particular, for that, we need to measure how strong the configurations that we generate are correlated with each other.
So this is Monte Carlo time.
This is Monte Carlo time, right, in autocorrelation in Monte Carlo time. So in particular, you see that, interestingly, as we increase the separation, so as we move to the right-hand side in this plot, the autocorrelation starts to increase dramatically, sometimes up to 2 or sometimes up to 2 orders of magnitude. So this tells you that non-local fluctuations have a significant effect, and you should always take this into. You should always watch out that you really sample all areas, in particular where you want to extract your scaling behavior. A second example, going to a much more non-local forcing with the choice y equals 6. So that's a decay with exponent minus 3 for the forcing correlator. Here, the same picture applies. The first row is at close to initial physical times. The second row is at late physical times in the configuration. You see the same type of behavior. You see that the autocorrelation increases as we go to large separations at late times. At initial times, of course, the forcing has not really built up the fluctuations yet. So in particular, the non-local, the nonlinear interactions in the system are not sufficient to provide the interesting effects at intermediate and large separations. So you see that the autocorrelations are also small here. Another interesting effect is if you take a look at the scaling exponents, we are a bit over-resolved, right? So it's a nice proof of principle, I guess, that you can also show that this really runs onto a plateau. So the configurations are really smooth. But then you have the problem that you have pushed out, right? So if you're over-resolved, you're wasting computational resources in the sense that the inertial range where you want to see that a plateau develops is pushed into the regime where autocorrelations are large and the error bars become large.
I mean, you must probably stress that it is a very small resolution.
Yeah, it's anyhow a very small resolution, so we really need everything.
How many points do you have in space?
This is 256, yeah, right. So it's a very small resolution. But nevertheless, you see that it's nice. There are some hints. I mean, this is a small ensemble to some sense. There are some hints that these 4 curves run onto a very similar value, which, well, you could guess is close to 1. But the errors here, of course, are overwhelming. So you really have to see how that develops. Yes, so finished right on time. So let me maybe conclude and offer some perspective on what we're doing. So what I've tried to emphasize is that Monte Carlo methods can also be used to look at genuine non-equilibrium dynamics. This is, of course, comes at a cost, but nevertheless, it provides us with the opportunity to explore what these methods have to offer. And in particular, this allows us to investigate algorithms that allow us to manipulate the system in such a way to highlight configurations that are of interest to us. So one thing I was mentioning earlier, Luca pointed it out, is that by choice of boundary conditions, we can really constrain the system and let the Monte Carlo take over and tell us which of those configurations are actually satisfying those constraints. Another principle that one can use is reweighing. Reweighing in the sense that we have an observable in mind, let's say a 2-point correlation function or a structure function, and we include this observable into the action and let the Monte Carlo decide which configurations give the maximal contribution in some sense to that observable, right? Which is very much in line with the original constructions of instantons in the framework of stochastic Burgers equation. So I pointed out that in contrast to usual applications of the hybrid Monte Carlo, for instance, in the context of lattice QCD, we need non-standard modifications of the update algorithm to even be able to sample these systems. So you could say that turbulence, I'm sure most of you have known this for a while, is a lot more difficult than QCD. In this sense, this is nothing else than the statement that we really have to cover a large range of scales to really resolve what is going on in the inertial range. Right? So I mentioned that this allows us to systematically explore possibilities in the framework of these Monte Carlo techniques. And one particularly important aspect thereof is that it's free of modeling assumptions, right? So in general, the only thing that you need to take care of is to derive the action for the model or the system of equations that you're interested in. So in principle, the same techniques apply for first-order hydrodynamics. For any other nonlinear dynamics that you might think of, you should take care that you do not fall into those pits I mentioned. So take care of discretization issues, how you choose your initial conditions. But as long as you make sure that those properties are satisfied, these algorithms are applicable to your problem. Yes, so of course, that concludes my talk. And I would, of course, be very happy to discuss or available for further questions. Thank you very much.